Hello everyone, I'm Russ Cox and I work at Google where I'm the tech lead of the Go programming language. An important part of our work on Go is making sure it's a secure programming environment, so we spend a lot of time on supply chain security concerns, both on our own and with other Google teams. My goal today is to give you a sense of Google's overall efforts in supply chain security and to highlight places where I think more research is needed. If you want to follow along or refer back to these slides, they're posted at go.dev/s as in short/ACM scored. The title of this talk is Open Source Supply Chain Security at Google. And a good first question is, what does that even mean exactly? Let's start with supply chain security. We're assuming we mean software here, even though we don't say it explicitly. What is a software supply chain? What does it mean to be secure? There's tons of hand-waving, but I'm not aware of any agreed-upon definition. To get ourselves started, suppose that supply chain security is engineering defenses against supply chain attacks. Now we have to define supply chain attacks, but at least that's more concrete. So what is a supply chain attack? Again, we all seem to know, but I'm not aware of an agreed-upon, crisp definition. Kim Zetter once defined a supply chain attack as the nefarious alteration of trusted software at its source. That's almost perfect. I would replace at its source with before delivery, since source can be ambiguous, and the alteration can happen in transit too. Before delivery is what fundamentally distinguishes a supply chain attack from a regular attack. If I break into your building and change the software on your computers at night, that's a regular attack. If I break into your software supplier and change it there, that's a supply chain attack. Before we get to software, here are two examples involving physical devices. Here's a hardware supply chain attack. In 1967, the United States Central Intelligence Agency convinced the Swiss company Crypto AG to sell electronic cryptographic devices with CIA-designed flaws to a variety of countries that the CIA wanted to be able to spy on. In fact, eventually the CIA bought the entire company and ran it directly. The operation ran for more than 50 years, only ending in 2018, and the devices were a critical source of intelligence for the US and its allies for decades. This was a hardware supply chain attack on these countries. In contrast, during World War II, the Allies discovered flaws in the design of the German Enigma encryption machines and used those flaws to design a process for decrypting the traffic. That is not a supply chain attack. It's just a design flaw, a vulnerability. Here's a software supply chain attack. Developers in China look for copies of Xcode on file sharing sites hosted in China, which are faster to download. In 2015, attackers posted a copy of Xcode with the linker nefariously altered to add malicious code to every iOS app it built. This modified Xcode, later named Xcode Ghost by security researchers, was downloaded and used by many app developers, and apps containing the malicious code were shipped to many iOS users. As another example, in 2012, according to news reports, attackers suspected to be from a China-linked hacking group broke into Juniper Networks and made a change to their VPN source code, replacing some critical constants in a random number generator. The effect was to create a backdoor that made it possible for the attackers to decrypt all VPN traffic to and from those devices. This is a supply chain attack because it changed the software before its delivery to customers. Ironically, the random number generator was backdoorable in the first place thanks to pressure from the United States government, which might be considered an algorithmic supply chain attack. As a final example, in September 2019, according to news reports, attackers suspected to be from a Russia-linked hacking group broke into the build servers at a company named SolarWinds. A few months later, they injected nefarious code into the build of a SolarWinds IT monitoring software called Orion. When users of Orion updated, the hacking group gained access to sensitive networks at a variety of government and corporate targets. None of these examples involve open source software. Let's define an open source supply chain attack as the nefarious alteration of a trusted open source component later used in a trusted program. Note that the trusted software does not need to be open source. Only the nefarious code has to be open source. For example, in November 2018, the NPM package event stream was discovered to contain obfuscated code that harvested Bitcoin wallets when linked into the Copay mobile app. Copay isn't open source, but EventStream is, so this is an open source supply chain attack. The code went undetected for 2.5 months. And do you know how the attackers made the change? They just asked the author if he wanted them to take over maintenance of the code, and he said, "Yes, please, thanks very much." That's clearly an open source software supply chain attack. But not all supply chain problems are attacks. In September 2021, Apple fixed a bug that allowed so-called zero-click takeovers of an iPhone device by sending an iMessage with a specially crafted image attachment. The attachment claimed to be a GIF, but was actually a PDF containing a JPEG-2 image. Apple's software used the open-source XPDF JPEG-2 decoder written in C, and that decoder did not properly validate the encoded Huffman trees in the image, making it possible to trigger bitwise operations on memory at attacker-controlled offsets beyond an allocated region. The attackers implemented an entire virtual CPU out of these bitwise operations, and then implemented code in that virtual instruction set to scan process memory, break out of the iMessage sandbox, and take over the phone. The buggy XPDF C code enabled this attack, but as far as we know, the bug was not nefariously introduced, so this would not be a supply chain attack. Later in 2021, some Minecraft players discovered that sending specially crafted chat messages caused Minecraft to download and execute Java code from remote servers. They used this for mostly harmless pranks on their friends. But attackers quickly realized that this behavior was an entirely intentional feature in a popular logging package called Log4j and weaponized it. The tech industry then spent their end-of-year holidays chasing down and updating all their usage of Log4j to avoid these remote execution attacks. The XPDF behavior was a bug, and the Log4j behavior was intended as a feature, but neither was a nefarious change, so they're not attacks. But they're also clearly an important part of supply chain security, so we need to broaden our definition. Let's call them vulnerabilities. Specifically, let's define an open source supply chain vulnerability as an exploitable weakness in trusted software caused by an open source component. Notice that the trusted software doesn't have to be open source. Minecraft isn't, but Log4j is, so we can still say Minecraft has an open source supply chain vulnerability. Now we can define open source supply chain security as the engineering of defenses against both open source supply chain attacks and open source supply chain vulnerabilities. So that's what this talk is about. That took a little while, but I think it was time well spent. That definition was far from clear to me, at least, when I started, and I hope it helped you too. On to open source supply chain security at Google. Before I do, 2 disclaimers. First, Google's a very large company, and while I'm talking about many of our efforts, some are not ready to be talked about publicly, and some did not fit into the talk. So don't take this as an exhaustive account of everything we do. Second, many excellent companies are doing work in this space, and it's natural for some of our work to overlap work being done elsewhere. Don't take any of this as criticism of other companies' efforts. Supply chain security has to be an industry-wide effort to make meaningful progress, but I'm here today to report work at Google. In general, our overall approach to software supply chain security has 3 parts: understanding the supply chain, strengthening it, and monitoring it. I'm going to talk about each of these in turn. If we're going to secure our software supply chain, first we have to understand what it is. And I don't mean the definition, although we haven't defined it yet. So let's define it as all the places where a supply chain attack might happen. But what I really mean by understanding the software supply chain is, what does it look like? Where might attacks happen? How can we represent or analyze a software supply chain? Part of the problem is that the word chain sounds simple, but a supply chain is like a fractal that's complex no matter how closely you look at it. At the lowest level, we can look at the build graph for a single program. This is the build dependency graph for Google's protocol buffer compiler, which is a relatively trivial C++ program as dependencies go. It reads text files and writes other text files. Each rectangle in this graph is an individual compiled library, and each line is an edge between a library and one of its dependencies. This graph has over 500 nodes and over 3,000 edges, and I'm not even showing the whole thing. In the inset, I've zoomed in on one small part, showing a few UTF-8 related libraries. Again, this is a trivial program. Real programs have much bigger graphs. A different kind of graph is the computers and services that source code passes through during a build. I drew this graph a couple years ago when I was looking at the supply chain security of the Go binary distribution downloads. Each of the rounded rectangles is a different program involved in preparing the binary distributions, at least at the time. The graph shows the places where nefarious alterations could be made, including machines hosted beyond Google's physical control. Drawing the graph helped us identify and eliminate those systems. Another kind of graph is the dependency graph showing which open source components are used by which other components in a build. Here's the dependency graph for Kubernetes, as plotted by Google's Open Source Insights project. There are hundreds of dots here, each one abstracting away some collection of relevant machines like on the previous slide. Each one of these is a different potential attack site, not to mention a potential source of vulnerabilities. We should be concerned with who has access to each of these projects, who might have access in the future, what infrastructure they use, and so on. For the most part, we don't have visibility into any of that, so we ignore it, but it's all still there. We are all struggling with a massive shift that has happened in the last 10 or 20 years in the software industry. For decades, software reuse was only a lofty goal. Now it's very real. Modern programming environments like Go, Node, and Rust have made it trivial to reuse work written by others. Kubernetes uses 3,000 packages from 200 dependency modules. Our instincts about responsible behaviors have not adapted to this new reality. The main goal of Open Source Insights, which you can visit at deps.dev, is to try to make the amount of reuse both visible and available for other analysis. On deps.dev, the Compare tab shows the dependency posture of two different versions. Here we can see that Kubernetes version 128.4 had two known security vulnerabilities. One is completely gone in 129.0 RC0, and the other is still present, even though the dependency containing it has been upgraded. I've shown you three different views of trying to understand the software supply chain. An important research question would be how to best put all this information into a machine-readable form so that we can analyze it all and understand where the weaknesses might be. For now, I think we understand certain parts well enough to identify important weaknesses and work on strengthening those. But more attention to systematic analysis of the supply chain would almost certainly identify new problems to address. Let's move on to strengthening the software supply chain. Remember our definitions. We want to engineer defenses against attacks and vulnerabilities. On the attack side, we want to find ways to remove as many potential attack sites as possible. And on the vulnerability side, we want to find the vulnerabilities before the attackers can use them, or even prevent them from occurring in the first place. We'll start with the attack side. Our most effective strengthening measure is cryptographic signatures, which make it impossible to nefariously alter code between signing and verifying. This completely removes download servers, proxies, and other network middleboxes as potential attack sites. However, it's not free. It introduces key distribution problems. Specifically, the verifier has to know who should have signed the code. The Go checksum database is a real-world example of cryptographic signatures for supply chain security, protecting millions of Go developers. The database holds the SHA-256 checksum of every version of every public Go package. Each database entry is signed by the database server's private key. The corresponding public key is hard-coded in the Go command source code, so key distribution piggybacks on the rest of the Go distribution. Every time the Go command downloads a new open source Go package, it looks up the expected checksum. There's a local checksum cache for dependencies in a given project, so network calls to the checksum server only happen for upgrades or adding new dependencies. But one way or another, every download is checked. This means all the proxies and other boxes between code hosting and your computer cannot be attack sites. Even an attack on the code hosting site cannot change old packages. There is, of course, the question of what checksum to put into the database. For Go, if the database hasn't recorded a specific package version yet, it fetches that code directly and stores the checksum for the code that it gets. This doesn't mean the code is trustworthy, but it does mean that the code can't change if anyone else downloads it on a different computer tomorrow or into the future. This immutability ensures that the entire Go ecosystem agrees on the meaning of Kubernetes version 128.4, which then serves as a foundation for any other work or analysis, including open source insights. Another project Google helped create is SigStore, which is a public, more open version of the Go checksum database. SigStore lets anyone publish a database record, and then clients can read a record back and verify it. SigStore explains itself with this diagram, where you have developers publishing code on the left and end users verifying code on the right. But really, this is not the way it would be used in practice. End users don't want to think about any of this. Instead, SigStore is a generic checksum database that a package ecosystem might use instead of running their own. As I understand it, the NPM ecosystem has done some preliminary integrations with SigStore, but it's not enabled by default, so it hasn't had much impact yet. But it's a good step, and hopefully that work will continue. Of course, there are computers running all these services, build machines, and so on, and those need to be secured. This is mostly regular computer security, not anything specific to supply chains, but it's an important prerequisite for all the fancier things. One important part of supply chain security is making sure that all the relevant build steps happen on dedicated, secured build systems, including cloud machines like Google Cloud Build or GitHub Actions, but not on individual engineering workstations. In general, dedicated build machines can be locked down better, since they don't have to run web browsers and chat software and whatever else engineers need for day-to-day work. At the same time, there's no free lunch. Engineering workstations do need to be secured too, or else attackers will just modify the source while the engineers are working on it. But builds are so central to software production that it's worth using hardened, dedicated machines. One way to reduce the importance of any individual build machine is to make sure builds are reproducible, meaning that if you build the same code multiple times with the same tools, you get the same outputs. Since computers are deterministic, it sounds like this should be trivial, but it's far too easy for contextual information like the build machine architecture or machine name, the names of temporary directories, or the current time to end up in some build output, making the overall build non-reproducible. Once you do have a reproducible build, you can run your build on multiple machines and check that the results match. We recently arranged for Go builds to be completely reproducible given only the source code, meaning that although a build needs some computer running some operating system and some earlier Go toolchain, none of those choices matter. You get the same distribution bits out whether you build on Linux or Windows or Mac, whether the build host is x86 or ARM, and so on. This very strong reproducibility makes it possible for others to easily verify that the binaries we post for download match our source code. We've also started logging those binaries in our checksum database and verifying them when the Go command downloads a new toolchain, so we know the downloads aren't being modified in transit. There are other important process improvements that can make open source code repositories and builds more secure. One of the most important is to remove unilateral access to source code and build systems. At Google, the rule is that any change to production code or production systems requires the coordination of at least 2 employees, just like the military needs 2 people to launch nuclear weapons. For a source code change, the 2 employees are typically a code author and code reviewer. For Go, as an open source project, if the code author is not a Google employee, then 2 Google employees must review the change. For access to our production systems, we have an internal authentication system that requires 2 employees to coordinate to get access to any production or build system. Process improvements like reproducible builds and 2-person approvals are important, as is securing build machines and code repositories. But it can be difficult to know whether a given project has done that. So another element of Google's approach to open source supply chain security has been to encourage projects to adopt and document their use of best practices. For builds, Google is one of the founding members of the Open Source Security Foundation, or OpenSSF, and has worked through that organization to define a standard called SALSA, which stands for Supply Chain Levels for Software Artifacts. SALSA defines 4 levels for the security of a build. Level 0 is the bottom, no guarantees whatsoever. At level 1, the build must run in an automated fashion and provide provenance, at least in the form of documentation showing how it was built. The automation eliminates manual mistakes and the provenance documents how to rebuild. At level 2, the provenance must itself be cryptographically signed and include a cryptographic hash of the build output, allowing consumers to verify that the output has not been tampered with after the fact. At level 3, the build must also run on a hardened build system. You could imagine even higher levels, but the fact is that most open source builds are not even automated in any standardized way, so they're at level 0. It doesn't matter yet what comes after level 3. SALSA was mentioned in the recent US executive order on cybersecurity, so you'll be hearing about it for many years to come. Another effort to draw attention to open source process improvements is security scorecards. You can run a scorecard program on your GitHub repository, and it will check for and score your use of various best practices. One example of a scorecard check is whether GitHub's branch protection feature is enabled. That feature stops project members from being able to push directly to a branch without code review. Another check is whether the repository's automated processes are using access tokens with unnecessary permissions. To the extent that engineers like to check boxes, scorecards end up being a kind of gamification of project security, incentivizing following best practices. Although there are checks for use of code review and use of static analysis tools, in general, scorecards are aimed at supply chain security, not code quality. I know there's a talk today finding no correlation between scorecard score and code quality, and that makes sense. Code quality is an independent goal, and it would need to be measured differently. I think that more research could be done about what is important to incentivize in a scorecard and what's not as important. And more research could be done about how much impact scorecards have on actual repository and supply chain security. Another recent project specifically watching for attacks is Caps Lock, which analyzes open source packages to understand what sensitive system services they might be using. In this example, at the top, Caps Lock says that the package I'm analyzing, which I didn't expect to use anything at all, turns out to read system state using os.getenv. At the bottom, it looks like Caps Lock is reporting that it lost the trail of indirections in a call to sort.search. So clearly there's more to be done. Caps Lock is only a few months old at this point, and it's still quite experimental. The vision is that you can use this tool to decide whether you want to take on a new dependency, and also to watch that existing dependencies don't start doing new things when you upgrade them. That is, you can lock in the capabilities allowed for a given dependency. If something like Caps Lock had existed for Java, it would have flagged that Log4j could download and execute code from remote servers, and maybe fewer people would have used Log4j, or that feature might have been removed sooner. If something like Caps Lock had existed for NPM, it would have flagged that the event stream upgrade had started reading files from local disk, namely Bitcoin wallets. It's worth pointing out an important limitation of Caps Lock specifically and capability systems in general. Code can operate within its expected capabilities and still do its actual job nefariously. For example, many services these days are configured using files written in YAML syntax. If you controlled the YAML parser used as a dependency in a major production system, you could probably find nefarious ways to adjust the configuration returned by the parser to change access control lists, firewall rules, and so on. And Xcode Ghost didn't do anything different from ordinary Xcode at the level of system calls or other capabilities. It just changed the meanings of the programs it was compiling. Capability systems, and even runtime enforced capability systems like sandboxes, are not a panacea for making it safe to use untrusted code, but they can still be an important tool. The strengthening discussion so far has been about protecting against intentional attacks. We also want to protect against accidental vulnerabilities, which are unfortunately far too common. I should mention in passing that Google funds external security work in a variety of ways, including bug bounties and patch rewards, and we also have an in-house team, Project Zero, dedicated to finding the hardest to find vulnerabilities in any important widely used software, not just Google's. And on the open source side, we have two different, surprisingly effective fuzzing efforts. Fuzzing presents programs with carefully designed random inputs over and over to try to get them to misbehave or crash. Google started and funds the OSS Fuzz project, which runs continuous fuzzing of important open source projects and reports the bugs they find. Since it started, OSS Fuzz has found over 10,000 vulnerabilities and over 36,000 bugs. Google also runs a separate fuzzing service, focused on trying to break operating systems with carefully designed random system calls. syscaller can check many operating systems, although it's focused mainly on Linux, where it has found almost 5,000 real kernel bugs that were fixed. As of this week, there are over 800 additional open issues that have not yet been fixed. These numbers terrify me. Even with modern techniques like coverage guidance, fuzzing is about as sophisticated as banging on your program with a rock. The effectiveness of fuzzing at finding vulnerabilities in modern software is a serious indictment of modern software practices. This month marks the 35th anniversary of Robert T. Morris's Internet Worm. At the time, Robert H. Morris, who was both his father and the chief scientist at the NSA, was quoted in the New York Times as saying, "It has raised the public awareness to a considerable degree. It is likely to make people more careful and more attentive to vulnerabilities in the future." In hindsight, I think it's fair to say that mostly didn't happen. We can't keep playing whack-a-mole with buffer overflow and use after free bugs. We have to find systematic ways to do better. Specifically, we need to stop using C and C++ and move to memory-safe languages. The NSA agrees with me. Last year, they advised making a strategic shift away from C and C++ to memory-safe languages. We created Go at Google specifically to avoid many of the problems with modern C and C++, and safety is one of the things we were focused on from the start. In Go, all array references are bounds checked, and at the language level, races cannot provoke arbitrary undefined behavior. Programmers can write type unsafe code, but they have to import the special package called unsafe to do that. Importing unsafe is one of the capabilities that Caps Lock watches, and in general, we've established a culture in the Go ecosystem of avoiding unsafe if at all possible. Another important new safe language is Rust, and Google has invested heavily in adoption of Rust too. Rust was adopted into Android as an official language in 2021, and since then, over 20% of the new code added to Android has been in Rust. That experience was one of the many reasons that Linux started accepting Rust code into the main kernel in 2022, and Chromium started accepting Rust code in 2023. Both Go and Rust are excellent ways to move on from C and C++. One way to evaluate the safety of a language is to look at what a serious vulnerability in that language looks like. In C and C++, the typical serious vulnerability is a buffer overflow, or use after free, that leads to remote code execution, like the Internet Worm or the iMessage hack. Java is a lot better than C++, since arrays are bounds checked, and like in Go, races cannot provoke arbitrary undefined behavior. Unfortunately, Java also provides very sophisticated code reflection and dynamic code loading, including code from other servers on the internet. And Java programmers find ways to use these that are powerful in ordinary use, but also enable powerful attacks. The result is that despite the language level safety, the typical serious Java vulnerability, like we saw in 2017 with Apache struts or in 2022 with Log4j, somehow still leads to remote code execution. On the other hand, the typical serious Go or Rust vulnerability is a malformed or large input that causes parsing code to panic or use too much CPU or memory, leading only to a denial of service attack. These exist in C, C++, and Java too. They're just less visible next to all the remote code execution attacks. So Go and Rust really seem to be demonstrably safer alternatives. It would be great to have more research to quantify these benefits, because to get companies to pay for conversion of all the critical C and C++ code in the world into safer languages, it would help to be able to make the case in terms of dollars. This would be a long-term strengthening, but a very effective one. Once we understand our software supply chain and have strengthened it as much as we can, we still need to monitor it for weaknesses. Monitoring needs to be an active process, so that at any moment, you can identify whether you're running code that has been recently identified as vulnerable or enabling an active attack. Clearly, an important aspect of monitoring is the Software Bill of Materials, or SBOM. But what is an SBOM? I don't know exactly. This seems to be another of those terms that we all hand-wave the definition of. The SBOM definitely includes the list of packages and versions used in the software. But what else is needed? Here's a definition from a US government working group. It says the amount and type of information in SBOM may vary. Great. So an SBOM is definitely a list of packages and versions, and beyond that, we have no idea. Here's why I say we have no idea. Remember that we are defending against attacks and vulnerabilities. For vulnerabilities, we absolutely need the list of packages and versions. And if we move on to actual attacks, then I can see you might want to know what machine built the binary in case you find out that the machine was compromised. But what machine generates the SBOM, and what if that machine is compromised? If an SBOM is meant to help respond to an attack, at the very least you have to be very careful about how it gets generated securely. And if the SBOM is not for attacks, then it seems like we can stop at packages and versions. Also, we saw the fractal complexity of describing the supply chain. How much does the SBOM include? Where does it stop? Figuring all this out seems like an important research topic. We should have a precise statement of what SBOMs are and are not meant to accomplish, and then based on that, should be able to identify what an SBOM should and should not include. Today, we don't have any of that. But moving on, because it is so important to understand what code is in a given program, every Go binary now includes a list of all the Go packages with source code that was compiled into the binary, which we could call an SBOM. There's no build option to omit this information or remove it after the fact, even though people have asked for that. You can rely on it being present in any compiled Go binary. This SBOM does not record any information about where the build was run, or who ran the build, or about tools that generated source files compiled into the binary. And a nefarious build machine might substitute different code than what it writes into the SBOM. But it's a good starting point, at least for scanning for accidental vulnerabilities. So let's assume that one way or another we know what's in our software. To check it for vulnerabilities, we also need a database of known vulnerabilities. For Go, we created and maintained the Go Vulnerability Database, which records information about every known Go vulnerability, which package is present in, and which versions of that package are vulnerable. Backing up from Go for a second, Google's Open Source Vulnerabilities Project, OSV for short, aims to construct a single database of all open source vulnerabilities with precise package and version information. The Go security team and the OSV team worked together to define a simple common vulnerability format that worked for both projects. And then we worked with other ecosystems to help them adopt it too. OSV is now the native format for vulnerabilities for Go, Rust, Python, and the GitHub Security Advisory Database, among others. And this comprehensive database is available for anyone who wants to use it. Back to Go, we have a per program SBOM and a database of vulnerabilities, so we can check whether your program has any of the known vulnerabilities. In fact, that's basically the only thing we all agree an SBOM is good for. So we wrote a tool called GoVulnCheck, shown running here. The first problem we encountered with GoVulnCheck was that there are too many false positives. For example, suppose my program uses code from Go package P, which has two functions f and v. F is fine, and v is vulnerable. My package only uses f, which is fine, but the SBOM in the Go binary is not terribly precise. It just says I'm using package P. So based on the SBOM, GoVulnCheck has to report the potential vulnerability, even though my program is not actually vulnerable. This kind of false positive turns out to happen quite a lot. As a first step toward reducing the false positives, the Go Vulnerability Database includes not just the package and version, but also the names of the specific functions in the package that are vulnerable. If those functions aren't called, the vulnerability is not present. So GoVulnCheck parses the stack unwinding tables in the Go binary to identify which functions appear in the binary. If the vulnerable function is not in the binary, there's no vulnerability. But this can still leave false positives. Quite often there are functions linked into binaries that are not reachable in practice. And that's what's happening on this slide. These are false positives, but from the binary, GoVulnCheck can't tell. If GoVulnCheck is given source code instead, it can use more sophisticated static analyses to eliminate more false positives. On this slide, GoVulnCheck is reporting the same vulnerabilities, but has explicitly flagged them as false positives. Reporting the false positives is important when GoVulnCheck's output is compared against other, less accurate tools. For example, GitHub's Dependabot and most other language-neutral tools use only the Go SBOM, so they have many false positives. GoVulnCheck can tell you whether a report from another tool about a critical vulnerability is an actual emergency. Vulnerability scanning isn't worth anything if no one uses it. So we've also integrated vulnerability scanning into the IDE experience. This screenshot shows a VS Code session editing the go.mod file where dependencies are listed. And there's a squiggly underline indicating a problem with a few of the dependencies. The user is about to click Run GoVulnCheck from the drop-down menu to see if they are true vulnerabilities or false positives. After running GoVulnCheck, the IDE reports that it is indeed a true positive, adding details about the specific vulnerability. Now the user can go back to the go.mod and use the menu option to update the dependency and resolve the vulnerability. The earlier in the development process we can provide this information, the easier it is for users to address these problems. Of course, vulnerabilities can become known after development is over and code is deployed. So you also need the ability to scan for vulnerabilities in the code that's already running in production. One approach is to scan all the container images for the containers you're running. Google Cloud provides the Artifact Analysis API to do this, and it scans Go binaries using GoVulnCheck. This is possible precisely because of the SBOM in every Go binary. Vulnerability scanning is far from a solved problem. More research is needed into how to avoid the many kinds of false positives and into effective ways to present the information. And then we also need better systems to automate the tracking and deployment of updates. When Log4j happened, people across the tech industry spent weeks finding and updating all the systems they had that were using vulnerable versions of Log4j. The response to the next Log4j needs to be no big deal at all. As an industry, we're not there yet. That's my overview of open source supply chain security at Google. I hope I've given you a sense of the breadth of our efforts and highlighted research questions that you might find interesting to explore. Before I finish, I want to zoom out even more and look at open source supply chain security over the last half century. In March 1972, the United States Air Force started a review of a Honeywell Multics system to understand whether it could be used in secure environments. The report was issued in mid-1974 and concluded that Multics was not secure, but better than its peers, and it might be a reasonable starting point for a secure system. The report raised the potential of adding a backdoor, which they called a trapdoor, to an innocent system call. If passed a specific, very unlikely argument, the system call allowed reading or writing an arbitrary word of kernel memory. That small, nefarious change would completely undermine the security of the system, and the report looked at the mechanics of how such a change might be made and hidden. One option is to make the change during distribution. The report mentions the US mail and insecure telephone lines as ways to intercept and modify the source code. I especially like the idea of mailing a custom patch out on forged stationery. Now, the specifics of this attack are antiquated, but this same thing still happens today. Xcode Ghost was exactly this kind of attack. Another point raised is that the trapdoor will be harder to detect if the binary is changed but not the source. This happens today too. Attackers change the package files uploaded to the NPM registry but leave the source code alone. One of the reasons NPM is exploring the use of SigStore is so GitHub can cryptographically attest that what was uploaded to NPM does match the source repository. Of course, the report points out, if the system is recompiled from source, the binary trapdoor will be lost. So an alternative would be to change the compiler to introduce the system call change. Now the Multics system call could be recompiled from clean source and would still get the backdoor. But if you recompiled the compiler and then recompiled the system call, you'd end up with a clean system. You probably know what comes next. The report pointed out that you could have the compiler add the compiler change too. And then if a nefarious compiler binary compiled clean sources, you'd still get a nefarious compiler binary. You probably knew this was coming because you've read Ken Thompson's 1983 Turing Award lecture, published in ACM as Reflections on Trusting Trust. In that lecture, Ken explained how after reading the Air Force report, he made a similar change in the Unix compiler to insert a backdoor into the login program, accepting a specific password for any account. Earlier this year, Ken sent me the actual compiler backdoor code, which I annotated and published. It's only 99 lines of code and a 20-line shell script, and I encourage you all to read it. So here we are in 2023. It's been 35 years since RTM's Internet Worm, 40 years since Ken's Turing Award lecture, and 50 years since the Multic security investigation. What has changed? The good news is that we know how to defend against backdoored compilers. Reproducible builds make it possible to compare a compiler built with itself against the same source code built with a different compiler. If they agree, then either everything is fine or the two compilers we used are both backdoored in exactly the same way. So as long as we can trust one of them, we've bootstrapped trust in the other. The bad news is that just about everything else is the same or worse. Far too much critical production code is written in C and C++, making accidental vulnerabilities far too common. The Air Force report was concerned with how a backdoor might elude careful source code scrutiny, but almost all of us run binary systems with no source code available. Even when source is available, as in open source operating systems like Linux, approximately no one checks that the distributed binaries match the source code. The source code is available for open source dependencies in our production programs, but there's too much to scrutinize. The programming environments for languages like Go, NPM, and Rust make it trivial to download and run source code published by strangers on the internet. We all do it, and no one is checking the code until there is a problem. No one needs a compiler backdoor. There are far easier ways to mount a supply chain attack, like asking politely if you can take over the code. On the other hand, given all our reckless behavior, there are far fewer problems than you would expect. Quite the opposite. We trust computers with nearly every aspect of our lives. We're all downloading and running code from strangers on the internet, and for the most part, nothing bad happens. Something about our security posture must be better than it seems, and exactly why that is would be an excellent research question. But even so, it would be nicer to live in a world where attacks required the sophistication of approaches like the compiler backdoor. So now that I've discouraged everyone, I'll try to end on a hopeful note. When the technology industry wants to improve security, they can do it. A decade ago, the majority of web traffic was unencrypted and unauthenticated, but thanks to a concerted effort to create good incentives and good tooling, today over 90% of typical user web browsing is encrypted and authenticated over HTTPS. A decade ago, passwords were stolen routinely, leading to account compromises. Today, passwords are still stolen routinely, but if you have two-factor authentication enabled, and especially if you use security keys, your accounts are secure. Over the course of 2023, GitHub rolled out a requirement that all users must use two-factor authentication, and the sky did not fall. In fact, in 2023, most major internet companies announced support for passkeys, eliminating passwords entirely. This would have been unthinkable not long ago. So we know that the industry can make security improvements when they're motivated and willing to pay for it. And Google is motivated. We're investing heavily in open source security through sponsoring the OpenSSF, vulnerability rewards, patch rewards, security subsidies, and more. Other companies are investing heavily too, and more help is always welcome. We also need research into the most effective changes that can be adopted and the justification for them. Even basic questions like what supply chain security means or what should be in an SBOM are still not answered precisely enough. With the recent US executive order on supply chain security and attention from other government agencies and other governments on both supply chain security and safe programming languages, it feels like change is coming. I hope that we will look back 10 years from now and marvel at how much better things are, and I hope you'll all help. Thank you very much.